Hello everyone and welcome to this final lecture within the series of Mathematics for Machine Learning. This one is going to be one of the most important videos within this lecture series where we are going to cover all the important concepts and topics within statistics that you will need for your data science or machine learning preparation. The idea or agenda behind this particular lecture is to gain an intuitive understanding behind the most important and frequently used topics within statistics without going too much deep into the nitty-gritty of the mathematical formulas, because most of the people, just by looking at the mathematical formula for a given topic, they tend to move away from understanding that topic or studying statistics. So we will focus more on understanding the concept throughout this statistics lecture. It is going to be an all-in-one jam-packed lecture where we are going to discuss a lot of things. So the length of the video might be comparatively bit longer. So I would suggest that you watch this one keeping a pen and paper handy with you so that you can keep on taking notes as well whenever required. So without any further delay, let's get started with the simple definition of statistics, which says it is a branch of mathematics that deals with the collection, analysis, interpretation and presentation of masses of numerical data. It allows you to make predictions, decisions, classifications by deriving knowledge from the data. And rather than memorizing this definition, we are going to focus more on understanding that how exactly statistics helps us to make predictions or decisions and how exactly we collect, analyze and interpret the data. So let's get started by understanding the frequently used terminologies within the field of statistics. And first start with sampling. By definition, it says sampling is the process of collecting a subset of data on which we want to perform analysis. For example, if I'll ask you to gather the data for all the students in a school, then you might have to go for collecting the data for all the students starting from class 1 to class 12. But let's say that instead of collecting the data from all the classes, you are collecting a subset of data. For example, you are collecting the data from the students only from the classes between 5 to 8. In that case, instead of going and collecting the data from class 1 to 12, you are collecting the data only from class 5 to 8. And this one is the sample from this entire population on the top. Which brings us to the next topic, which is sample versus population, which we have already understood. Population is the entire data set that we have discussed over here, like from class 1 to 12, from where the sample are taken, which is this one for instance. Then we have sample frame. It is a list from which sample is selected. For example, unemployed people. So if we talk about the people in our country, we know that we have a huge population. But let's say that you have been asked to collect the data only from the unemployed people. In that case, unemployed people will become the sample frame that you are given. Similarly, among all the students within our country, let's say you are collecting the data only from the medical students. Then medical students becomes the sample frame for which now you will collect the sample. And the last example could be female employees of an organization. So among all the employees, let's say you are collecting the data only for the female employees. In that case, female employee will become the sample frame for which you are collecting the sample. Then we have sampling error. It is an error that leads to our sample not accurately representing our population. So let's say that we are doing a survey in a company and you are being asked to collect the feedback from all the employees of that organization. Of course, practically you will not reach out to each and every employee of the organization, but you will have to go for a subset of data, which is also called the sampling out of the entire population. And when we talk about sampling, it has to be absolutely unbiased. So let's say in an organization, you have freshers, you have employees with the experience of, let's say 2 to 3 years. And let's say you also have employees of a seniority within 5 to 10 years as well. Then ideally your sample frame should cover the data from all of these kind of categories. But let's say you are taking out the sample or data only for fresher. In that case, the data collected only from this particular sample frame will not accurately represent the data for the entire organization. And this is what actually sampling error means. It is an error that leads to our sample not accurately representing our population. So of course, if you are collecting the sample only from the freshers, that will not accurately represent the people or employees from the other two categories. Then we have non-sampling error. It occurs due to poor sample design, inaccurate measurement, and bias in data collection. Let's try to understand this. Poor sample design is something that we have covered on the top, that instead of taking out a sample or subset of data that accurately represents the entire population, your sample design is poor. Inaccurate measurement means that, let's say that you are collecting the data for the height of students, and for few hundred students the height has been recorded in centimeters, for few students it has been recorded in inches, and maybe for few students it has been recorded in meters. So this inaccurate measurement will also lead to non-sampling error. Bias in data collection means that you have some biasness within your sample. For example, let's say you are collecting some data within an organization, and 70% of your data is coming from the female employees and only 30% of the entire sample is coming from the male employees. This is called the biasness in your data collection. So I hope that the idea of sampling error and non-sampling error is now clear to you. Let's move forward to random sampling. It is the process of selecting a subset or sample from a population in such a way that every data point is equally likely to be included in the sample. So consider this example over here. If you are taking a random sampling, then it should happen in such a way that 50% of the data or the sample should be coming from the female employees and rest 50% should be coming from male employees. Then it will be an accurate representation of random sample. Moving on, next we have stratified sample. So it is the process of dividing your samples into layers or groups and then performing random sampling for each group. So let's say you have a huge population where you are supposed to do the survey, but instead of going for the entire population, you are taking the subset or sample by dividing it into layers. Let's say from class 1 to 5 you have one layer, then class 5 to 8 you have another layer or group, and then from class 8 to 12 you have another layer, and then you are performing random sampling for each of this group. As simple as that. And finally, we have systematic sampling. It is the process of selecting your sample by picking every kth element from your population. You don't need a list, and to be specific, sample list in order to do this. What I mean to say is, let's say that we have 100 students in our school. Then what you have decided to do, going by the systematic sampling, that going by the kth element, you are going to consider the data from every third student, or it could be every second student as well. So let's say instead of taking the data or collecting the data from each and every student, you are collecting the data from every kth student within your entire population. And I hope these terminologies are now clear to you. So let's move on to the next topic. Let's cover central tendencies. If we go by the definition, then it says it is used to indicate where does the middle or center of the distribution of our data lies. Let's try to understand this further. Central tendencies are of three types. First is mean, then median, and then mode. Let's understand mean first. Let's say that we have these data points within our data frame. So we have 5 data points in total. So n is equals to 5. If we take out the sum, then it will be 75. And mean is nothing but the average of this entire data frame, which is n divided by sum. I think it is wrong. It should be actually sum divided by the n. So we have 75 divided by 5. So it should be sum divided by the number of data points, which is equals to 15. So 15 is the mean or average for our data set over here. If we talk about the median, then it is the data point which is falling exactly at the middle of your data, which is 3 over here. And if you pay attention, we have 2 data points on top of it and 2 data points at the bottom of it. But you might wonder that what if we have 6 data points or even number of data points within our data frame? In that case, both of these numbers will become the median, and we will still have 2 data points on the top of it and 2 data points on the bottom of it. As simple as that. And finally, let's cover mode as well, which is nothing but the most frequent data point within our data. For example, over here, the occurrence of 2 is most frequent. First is here, then here, here, and here. So the mode will be equals to number 2 over here. These are very fundamental and basic concepts within statistics, and it is the least that you are considered to be understand. And hopefully these ideas are now clear to you. So let's move on to the next topic. Let's quickly discover the idea of discrete frequency distribution. By saying discrete numbers, we mean, for instance, that there are 8 students whose height has been measured exactly as 150 centimeter, 12 students where height has been recorded exactly as 140 centimeter, and so on. And these are discrete numbers. On the other side, if we will move on to the next topic, which is continuous frequency distribution, then you will see we have 15 students whose height has been recorded somewhere between 100 to 120 centimeters, which means height of a given student could be 110.5 centimeter as well, which is definitely not a discrete number. Again, for 25 students, the height has been recorded between 120 to 135 centimeters, which means within this range, the height could be anything, even in fraction, let's say 22.55 centimeter. So this is the fundamental idea or concept behind discrete and continuous frequency distribution. Now let's understand about variation, which is nothing but the method which is used to understand that how data is dispersed or spread out. There are 3 different popular methods of checking the variation. First is range, second is quartiles or quantiles, and the third is variance. Let's explore all of them one by one. So first is range, which tells us the distance between the lowest and highest values in our data. So let's say we have these 7 data points within our data set. If you will observe, the lowest is 10 and highest is 20, which essentially means that a range is between 10 to 20 for this particular data set. Very much simple and straightforward. The next and slightly tricky concept is quartiles. Quartiles are used to break the data into 4 parts, and this method is used to tackle outliers as well. Let's first understand that how exactly we are breaking the data into 4 parts. Let's say that within our data set, the range is between 200 to 400. In that case, if we try to break this data into 4 parts, the first bucket will have the data points between 200 to 250. The second bucket will have the data points between 250 or let's say 251 to 300. In the third bucket, we will have from 301 to 350. And finally, in the final bucket, we will have data points from 351 to 400. And this is how we break any given data into 4 parts as per the idea of quartiles. So I will first quickly erase it. And next is that it is also used to tackle outliers. Let's understand how. If you'll see here, interquartile range or IQR is the difference between the lower and upper quartile. So if we are breaking the data into 4 parts, let's say 1, 2, 3 and 4, the first bucket will have 25% or the first 25% of the data. The second one will have 25 to 50%. The third one will have 50 to 75% of the data, and the fourth one will have 75 to 100% of the data. And the idea of IQR range is nothing but excluding the data from the first bucket and from the last bucket, and only this middle part is considered in order to tackle the outliers. Let's try to consider this thing with another example. So I will quickly erase this one. And let's say we conducted a test in a class and the marks obtained by the students ranges between 200 to 800. Let's divide this entire number in 4 quartiles. So starting from 200 to 350 will be the first quartile. From 350 to 500 will be the second quartile. From 500 to 650 will be the third quartile. And from 650 to 800 will be the fourth quartile. And let's say out of 20 students, 17 students have scored between the range of second and third quartile. There is only one poor student who have scored between this range of first quartile, and only 2 students have scored exceptionally high within this last quartile. So evidently these 2 students or these 2 groups becomes the exceptions or outliers. And if we are doing the survey, then we will consider only this group of students. And this is how excluding this first part and last part is helping us to tackle outliers. So I hope that with this explanation, your idea towards quartiles and how the interquartile range helps us to tackle outliers is now clear to you. I will quickly erase this one as well. Then it says quartiles can be expressed in percentiles, where first quartile is 25th percentile, second one is 50th percentile, third quartile is 75th percentile. By the way, if you're someone who is not familiar with the concept of percentile, then please quickly have a look on this one as well. Percentile is a score that is used to describe a value below which some observations fall. So let's say if you are competing with 100 students and I am telling you that you stand on 60th percentile, in that case it means that 60% of the students have scored lower than you. So let's say over here, if you are on this point 60th percentile, then it means this much students have scored lower than you, and this is something that you can consider as your rank. And same thing is also being explained by the definition over here, that if X is at 60th percentile, it means that 60% of other data points from our sample are below X. Hence, the first quartile is 25th percentile because 25% of the other data points falls below this observation, and second quartile is 50th and second quartile is 50th percentile, and so on. So now we have also covered the concept of percentile as well. Let's quickly move forward to the topic of variance. Speaking about variance, let's first cover standard variance, which is a measure of how far a set of numbers are spread out from their average value, which I believe not that difficult to understand. So let's say that you have a data set like this, which ranges between 1 to 200, which is nothing but the lowest and highest value. And if their mean is, let's say, 50, in that case, standard variance helps us to understand that how far the set of numbers are actually spread out from their mean. Pretty much straightforward, no rocket science. And next is standard deviation, which is used to express the magnitude by which the members of a group differ from the mean value of a group. And if you will pay attention to this figure, the formula on the left side is used to calculate the sample variance, and on the right side it is used to calculate the sample standard deviation. If you are doing it for the population instead of the sample, then instead of having n-1 in the denominator, you can keep only n. Key things to remember that standard deviation is nothing but the square root of standard variance, which you can obviously understand by looking at the formulas, that if you pay attention to the left hand side and then compare it with the right hand side formula, then you will observe that the superscript from S is moving to the other side as the square root for standard deviation, and hence standard deviation is nothing but the square root for standard variance. You may also get asked in an interview that what is the coefficient of variance or relative standard deviation. It is nothing but a value when you divide standard deviation by the mean. And with this topic, we have covered all the methods of variation that we discussed earlier. Now let's cover about normal distribution or Gaussian distribution. Essentially the same thing. If we go by the definition, then it says this term is used to represent a data which looks very much like a bell curve when plotted on screen. Usually comes with a mean of 0 and standard deviation of 1. And when we have a mean of 0 and standard deviation of 1, at that time it is actually called a standard normal distribution, which looks like a bell curve when plotted, something like this. We will also try to understand all these numbers that you can see on the figure. So let's move ahead one by one and let's try to understand empirical rule. It is the term which is used to remember the percentage of value that falls within a band around the mean of a normally distributed data set. If you will pay close attention to this figure, then this is the point of mean, and this is the first band, and this is the second band. And in total, we have around 68% of the data from this entire population falling within the first band. If we move ahead to the second standard deviation, then we will have almost 95 to 96% of the entire data falling within this area. And this is something which is nicely explained by the empirical rule. And this area of the third standard deviation is also used, or you can say a very common technique to tackle outliers. And it also makes sense because the majority of the data is falling within the area of second standard deviation. Okay, I will quickly erase everything to make it look nicer and cleaner. Moving ahead, next we have ZScore, which is a measure of understanding that how many standard deviations below or above the population mean a raw score data point is falling. So let's try to understand this better from this figure only. Let's say that within a data set, I give you a random number, it could be anything, let's consider it X, and I ask you to check or find out that where exactly within this distribution, the data point X is falling in. It could fall somewhere over here at the 1.5 standard deviation, or maybe somewhere here at 0.5 standard deviation, or maybe here minus 0.7 standard deviation. In order to find it out, Z-score is something that we use in statistics. So there is a simple formula that you can see over here, that the Z-score will be equals to the raw number, which is X, minus mu, which is the mean of the entire data set, divided by the standard deviation. If you do this calculation, it will give you the output to find out that where exactly within the normal distribution your raw score is falling in. Next, we are going to cover log normal distribution. So consider a data set X, and let's say that we calculate the log of each and every data point within X. So let's say that we have a data set X which has 5 data points, and if we are calculating the log of all of the values individually one by one, and when we are trying to plot all the log values on the screen, we get a bell-shaped curve like this, just like a normal distribution. In that case, this data set X will be considered as equivalent to log normal distribution. It is more clear by the definition, which says consider a data set X. If we calculate the log of every data point within X and we get a bell curve after plotting it, then X belongs to log normal distribution. And one interesting property of a log normal distribution, if you will simply try to do a Google search, if you will try to compare it with a normal distribution, then you will find out that compared to a normal distribution, log normal distribution will be skewed towards the left, which is an interesting property which makes it different from a normal distribution. So I hope that you are clear till this point. If you have any confusion, then I highly suggest that you move slightly back and go through the explanation one more time. Otherwise, if you are clear till this point, then well and good. Let's move further. Now we will cover one of the most frequently asked topic in data science interviews, which is central limit theorem. Let's try to understand this explanation over here. Consider taking out 35 random samples from a population of random values X, and let X dash be the mean of X, and then let X1 dash, X2 dash, X3 dash up to X35 dash be the mean of all 35 samples that we have collected from the population X. Then, as per the central limit theorem, we will get a normal distribution or bell curved shape when all these mean values from all our 35 samples are plotted, which essentially means if you're plotting all the mean values from all the 35 samples, it will give you a normal distribution curve or bell curve. And another interesting thing is the average from all these mean values will be equivalent to X dash, which is nothing but the mean of our population. If you are still not clear on this, let me give you another example. Let's say that we have a population X and the mean of this population or data set is X dash. And let's say that we are collecting 5 samples out of it. First is A, then B, then C, then D, and then E. Although usually, as per the central limit theorem, you do not collect 5 samples, there has to be at least 30 or 32 samples. But for simplicity purpose and to keep the explanation basic, I am considering only 5 samples. So let's say the mean from all these samples, the first sample mean, let it represent by A dash, then B dash, then C dash, and so on. Then what the central limit theorem is saying, if you will plot all these values like A dash, B dash, C dash, D dash and E dash, after plotting it on your screen, you will get a bell curve shape. This is first thing. Second thing is, if you will take the mean of all these values and let that be S dash, then this S dash will be equivalent to X dash, which is nothing but the mean of our population. And this is the core idea of central limit theorem. If you found this explanation or example helpful, then you can also use this example in your interview if you are being asked about the central limit theorem. And now let's move on to the next topic. Let's quickly cover about covariance as well. So let's consider this example over here, where on the x-axis we have the selling of ice cream, and on the y-axis we have temperature of the weather. And as we know, as the temperature increases in the summer, the ice cream selling also increases. So it goes something like this, and this relation between these two variables is called the covariance, and this was an example of a positive covariance. Similarly, if we take a similar kind of example with temperature of the weather and the, let's say, heaters that we use in our bedroom in the winters. So if the temperature is increasing, of course the cell will decrease. So here the figure will look something like this, which essentially means when the temperature is at lowest, which means in the winters, the selling of the heater goes higher. Similarly, when the temperature is at the higher side, comparatively the selling of the heater goes on the lower side. So this was an example of negative covariance. And now if you will look at the figure, it will make more sense that we have positive, negative or no covariance, and this will be the formula to calculate the covariance. Of course, I have taken it from Google. There is a breakdown given for all the components of the formula, so feel free to have a look. Now let's move on to the next topic, which is Pearson correlation coefficient. We have seen that what is a covariance, which is nothing but the method of understanding the direction of linear relationship between two variables. However, when it comes to understanding the magnitude or strength of their relation, we use the concept of Pearson correlation coefficient. So in the previous example, we were able to understand if the correlation between two variables, if it is positive or negative. But if we talk about either of them, let's say a positive covariance, then two variables may have the covariance of different magnitude. One may have a covariance of lesser magnitude like this, or one may have a covariance of higher magnitude, maybe like something like this. So this could be a covariance of, let's say, 0.55, and the other one could be a covariance of, let's say, 0.75. And these are made up numbers, so please avoid finding any logic behind it. And this is the core idea of Pearson correlation coefficient. This actually helps us to find out the magnitude or the strength of the relation between two variables, and this is the formula of measuring the correlation. Then we have Spearman ranks correlation coefficient as the next topic, and I have taken this entire figure and explanation from Wikipedia because I found a very nice explanation over there. So I will try to give you a proper breakdown for this, and let's try to understand what exactly is a Spearman's rank correlation coefficient. So over here in the data set, if you pay attention to the first column, we have the IQ recorded for each and every individual corresponding to the hours of TV per week they watch. So for example, an individual with an IQ of 100 watches TV for 27 hours per week. In the third column, we are checking the rank of XI, which is nothing but the IQ. For example, if we arrange this column in increasing order, then 86 is the lowest, hence it has a rank of 1. Similarly, in the fourth column, we are checking the rank of YI, which is nothing but the hours of TV per week. So again, if we arrange this column in increasing order, then 2 will have the rank of 1, and so on for each and every value. For the first two columns, rank has been assigned to the third and fourth column, and after assigning the rank in the third and fourth column, what we are actually checking is that what is the correlation between the ranks of these two columns, and this is actually the core idea of Spearman's rank correlation coefficient, to check the correlation between the ranks of two variables, and this will be the formula for Spearman's rank correlation coefficient. Now let's discuss about the concept of p-value, null hypothesis and confidence interval. Let's try to understand this with a simple example, and assume that you go to bed at 10 p.m. every day for most of the time. Let's say for 95% of the time, it is very usual that you will go to bed by 10 p.m. There is a very little chance of you going to bed before this time, let's say somewhere around 8 p.m. And similarly, chances are very slim that you will be late in order to go to bed like 11 or 12 p.m. And now with the help of this example, it will be very easier to understand the concepts of p-value, null hypothesis and confidence interval. First of all, you going to bed by 10 p.m. becomes the null hypothesis, and then you being late or being too early for going to bed will become the alternate hypothesis. The chances of the occurrence for the null hypothesis is the confidence interval that we have for 95%, and combining these two values, like 2.5 here on the left hand side and 2.5 here on the right hand side, which in total results to 5%, becomes the p-value for here in this situation. And within the field of statistics, many a time you will be given a situation where you will have to do different types of tests in order to find out the chances of a null hypothesis or alternate hypothesis to be true. And the step-by-step approach for that test is something that we are going to discuss next. So the first thing is to define the null hypothesis and alternate hypothesis, which we have understood in the previous example. Then, based on the circumstance, we perform different kind of experiments or hypothesis tests like t-test, z-test, chi-square test or ANOVA test. Please let me know in the comment section if you want me to cover these tests separately in different lecture. And eventually what these tests helps us to understand is whether we need to reject the null hypothesis and accept the alternate hypothesis, which we will do if the test value falls in the extreme end, as we have seen in the previous example, or we need to accept the null hypothesis and reject the alternate hypothesis if the test value falls within the confidence interval that we have also covered in the previous example, as we had a confidence interval of 95% over here in the previous situation that we discussed earlier. And this is how we finally get into a conclusion if we are going to select the null hypothesis or the alternate hypothesis. So that is it for today's lecture. I understand that we have covered a lot of things within this particular lecture, and this might be slightly overwhelming for the people who are covering statistics for the first time. But essentially, this lecture also covers all the topics or important concepts that you will require to work further in your data analysis or data science career or studies, or also the topics that you will be asked frequently in your interviews. Consider hitting the subscribe button if you are new to the channel, and drop a like below if you have found this video helpful. And hopefully I will see you in the next lecture. Thank you very much for your time today. Take care.